Okay, you can notice the red light at the top left corner of the application. We have just started the recording. Good morning and good evening to all, and welcome to the Data-Driven Community virtual meeting. A few words about the Data-Driven Community. As you can notice at our website, this is a screenshot of the website. We are managing two branches of activity. If you scroll down the page a bit, you can see the upcoming event. On the right side of the page, you can check the upcoming weekly meetings of the Cloud Data-Driven User Group, like today. The second branch of activity we run is an annual conference. It is a joint conference organized by multiple data platform user group, and it's called the Future Data-Driven Summit. Don't delay getting your early registration. It's not so early. It's about 2 months from now. Early registration can get you to a special list. You will get, of course, update and more information, but there are also a raffle that we run from time to time, and we give gift swags to people that were registered early. So if you register now, you can participate in all the future raffles till the day of the event. The first raffle of the early registration was 1 week ago. Please feel free to use the chat during the meeting for questions and for discussions as well. This is a user group meeting, meaning that it's more flexible, it's not a conference. So feel free today to use the chat. You also will the reaction. Please do not use your microphone at this time. This is my time. You are also welcome to use the reactions. It doesn't interfere with the course of the meeting. This is exactly what I mentioned. The microphone does interfere. Do not use it. You can use the chat and the reaction. If you see something that you love, you like, or you just want to clap hands virtually, do it freely. You are more than welcome to contact any of the community board if you have any question or suggestion for the future. I would be honored right now to present Jen Joseph. First of all, he is the founder of the community, and obviously is the first co-admin. Jen is working at Microsoft, and basically everything that we do, he leads us. Anna Weekly is the second co-admin, and myself, my name is Ronen Arieli. I'm from Israel. I work as a senior consultant in the field of data platforms and architecture of enterprise-level systems. I'm the third co-admin of the Data-Driven Community, and I will be hosting this meeting today. So those are the board members, and today I'm honored to present you Iuliana, who is not new in our community. She spoke about 1 year ago, and she's coming back today with a very interesting topic. Iuliana, you can share your screen. You can add some word about yourself and take control.
Hello, my name is Iuliana. I live in Romania. I have 9+ years of experience in data platform, mainly working on Microsoft tech stack. And I do also have here some links if you'd like to get in touch with me. And today we'll speak about Spark structure streaming. And I think we can start with the presentation. Okay. So as I mentioned, we will speak about the sparse structure streaming. But before speaking about the sparse structure streaming, let's review a bit the traditional data processing methods, which are not that old because they are also used nowadays, but it depends on the case. And we have the batch processing. The batch processing, here we have the full batch processing and the incremental batch processing. When it comes to the full batch processing, we reprocess the entire data set every time, which means that we cannot reprocess data sets that are very large, or we cannot reprocess them very often. And that's why this is suitable for those cases where we need to import, let's say, data sets that do not change that often. Let's suppose we want to import a mapping rule file into a table, and we are going to leave it as is for 10 years. Or some ad hoc data imports. It's very good for that, but not to, let's say, retrieve this data very often. For retrieving the data more often, we have the incremental batch processing, which is very nice because instead of processing everything over and over again, we extract only the data that has been modified since the last extract. This is suitable for data warehouses because when we go to the source systems, we have timestamps or IDs that we can use to keep track of the changes. Let's say the next time we want to retrieve the data, we just add a filter like select the data with the timestamp higher than the latest that we retrieved in the previous run, or the ID. But because we need to do some cleanups, we need to keep track of those fields, we have these housekeeping activities, let's put it that way, and it takes some time. We can do this daily, monthly, weekly, twice a day, but to extract the data, do the needed transformations, and update the reports, it takes some time. And because data is being collected more and more, it appeared the need to process large volumes of data very fast and to have the reports updated immediately. So to do not have a discrepancy between the data transfer and let's say the logic that is used for the final reports. And because of this growing demand, it appeared the need to use a more powerful engine. And this is sparse structure streaming. So it was adopted more and more because there are a lot of industries that improved their business decisions by analyzing immediate data and large volumes of data. And even though the name does not sound that intuitive, it processes the data in micro batches. So it combines the streaming processing with the batch processing into one single unit. And it processes small batches at short, regular intervals, and we have latencies of 100 milliseconds, which is very nice if we want to process data in real time or near real time. And they have also introduced the continuous processing mode, which has latencies of 1 millisecond, but is still in experimental phase. So that's why it will not be the focus in this presentation. But how does Spark processes the data stream? It treats a live data stream as an unbounded table. So this is our source, and we have new data that comes into the source, and it looks like if it's being appended to an ever-growing source. Then we have new data 2, the same thing, and new data 3, the same thing, and so on and so forth.
You muted yourself.
Sorry?
He was muted.
Oh,
okay.
So I spoke on mute?
No, it was okay in the last slide. Just when you move to this slide, somehow you muted yourself by mistake.
Could you please tell me from which slide?
This one. Start from this slide.
This one.
Because
okay.
It was okay, like 10 seconds ago.
Okay, thank you so much for this. Well, so what is a data stream? Is any source that grows over time. Even if we talk about files in the cloud storage, we can have CSV files, we can have JSON files in Azure, in AWS, in Google Cloud Storage. Even if we talk about events, let's suppose we want to track hashtags on Twitter, events written on Kafka topics or Azure Event Hub, and then we get them in Databricks using Spark structure streaming, we read the data from those topics. Or we can talk about CDC feeds. We can enable the CDC on, let's say, on-prem SQL Server. Then we can propagate the insert update deletes to a Kafka topic and read from the Kafka topic CDC feeds. So any source that grows over time and it expands a lot. Now, how can we read this data and how can we write this data? Well, when we read the data from a table in Spark, we use spark.read. But when we read streaming data, we will use spark.readStream. We have this keyword, the read stream for reading the streaming data and the write stream for writing the streaming data. And in this case, we read from a streaming table. So we have spark.readStream.table and the name of the table, where in a streaming data frame. If we have here spark.read, then that's a static data frame. Now, because we have specified the read stream, this is a streaming data frame. While for the write, we have the streaming df, which is this one from here, that write stream, along with some properties that we're going to discuss in the next slides, that table and the name of the table. The stream starts not when we read from a streaming table. The stream starts at the write. It starts either when we have this dot table, because the streaming object is being created, or when we call dot start. But because here we write to a table, we have that table. If we write to a path, we have that start. We need to start the stream. And we will have some examples in this presentation and some demos where we'll also have the start. But the stream does not start here. It starts here. And because I mentioned about those properties, in this slide we have trigger processing time. And trigger processing time, 3 minutes in this example. We have default, unspecified. We have processing time. We can specify any other value, trigger once, and available now. All of this give us more control on how often we want the streaming flow to run. If we don't specify any trigger, then the data is processed in micro batches. And once a micro batch finishes, then the other will start. If we specify processing time 2 minutes or 10 minutes or 1 hour, then the data is being processed every 2 minutes. Let's suppose that my trigger runs at minute 2, but at minute 3, I get some events. Those events will not be processed. They will be processed at minute 4, because this is how I tell the trigger when to run. We have the trigger once true. This one is deprecated, but I added here because I saw that it's still used somehow, which means that it processes all available data in a single batch, and then it stops. And we have the available now true, which is almost the same with the once true, but this one processes all available data in possibly multiple micro batches, and then it stops. This one is not deprecated, and is very good if you would like to run the streaming flow, let's say, with available now and get everything that is available, and then schedule it once a day if you want to, let's say, combine the streaming with the traditional methods. And we have also the output modes. The append mode, which is the default one, so only the new rows from the source will be propagated to the target. And we have that output mode append. We have the complete mode, which is supported only for the aggregation queries, and means that the target table is overwritten. And we have the update mode used to upsert the data. Output mode that update. These are all available output modes, but they might differ and might not be supported for some things. So just check the official documentation for Kafka Sync. I saw that all of them are supported, but there are also others where they are where not all of them are supported. And the checkpoints, which are very important because they track the progress of the stream. So this is how we know what was processed and what remains to be processed. This is the reason why we don't get duplicates. Even though our stream fails, it recovers automatically and it knows where it left off. And apart from that, it stores the stream state. The stream state means that every time we have aggregations, it keeps track of those values, variables, so that the next time where, let's say we have transactions and we want to count the number of transactions received within one hour. The first transaction comes in, then the second and the third. So it keeps this count into the state. And this is very important. It maintains all the intermediate data. And an important note, the same checkpoint cannot be used by two separate streams, which means that each stream has its own checkpoint. And let's have also a quick demo on this. In this first demo, basically I will show what we have discussed. Here I have a cleanup because I want to have the tables dropped before the creation, just to make sure everything is cleaned up. So let me run it. Okay, and here what do? I create a table, a bronze table. I insert two records in the bronze table. So two transactions, transaction 1 and transaction 2, with customer 1 and customer 2, and the date. Then I create another table, silver transactions, with transaction ID, customer ID, transaction date. So it's almost the same as the first one, but the ID is not called ID anymore, it's called customer ID. A small transformation. For reading the data from the bronze transaction table, I use spark.readStream, .format delta, .table bronze transactions. And I read the data from the bronze transactions table to a streaming data frame called bronze stream. And I use this bronze stream to perform a quick transformation to rename this ID column to customer ID. So I can do also this. Then I want to write this data to the output. In order to write this data to the output, I have the bronze transformed, which is streaming data frame, write stream, format delta, output mode append, the default one, trigger. I will not specify the trigger, this is commented. Option, I add a checkpoint, and I add a table, silver transactions. So I have run the first cleanup. I have run also this table creation. Let me run this. As I mentioned, the stream starts now. The stream didn't start at this point, but it starts now. Because I didn't specify any trigger, it runs continuously, and it processes data in micro batches, one by one. Let me select data from silver transactions. I have these 2 transactions that I inserted here. Once it starts, it processes all the data that it has. Okay, now the streaming is running. Let's insert another 2 records, so transaction 3 and transaction 4. This is also a dashboard that shows us input records per second, processing rate, batch duration, and when I inserted 2 records, we have here and we can see 2 records inserted. Now checking the silver transaction table, we have transaction 3 and transaction 4 added here. So we don't have any duplicates because in the source table, now we have 4 transactions and we can consider that we run it again. In fact, we didn't run it again. We have the checkpoint and it knows where it left off. Let's insert another 2 transactions, 5 and 6. They are processed and we have them here. Now, in order to stop the stream, we can either click on the interrupt or the query.stop. Silver stream append, which is its name, and it's stopped, as you can see. Okay, now let's get back to the presentation. We started from here. Now let's talk about the data ingestion from files, because we discussed about how we let's say how we transfer data from a streaming table to another streaming table. Now let's review it a bit. How can we transfer data from files? Here we have two options. We have the copy into and we have the autoloader. The copy into loads the data incrementally into the Delta Lake tables, and it's very suitable for small data sets. It has a SQL-like syntax, so it's very friendly, but it requires manual triggering or scheduling. So it doesn't process it doesn't process the data in real time or near real time. But we have the autoloader, which leverages structured streaming and is very suitable for real-time and near real-time data ingestion. It automatically detects the data as it arrives. So we have one file, it processes the file, then the second file comes in, it processes the data from the second file, and so on and so forth. And it provides a structured streaming source called cloud files. So in order to use it, we will have the spark.readstream, and we will add in the format cloud files. Then we have the option, what is the format of the cloud files. It's the format of the file here. Let's say it's JSON file. We need to specify the path where those files are located. Then on the right stream, the checkpoint location, because it leverages structured streaming, so we have also checkpoints, and the table name. And this is how it processes the files from source to destination without creating any duplicates. We can have various file formats, so from JSON, CSV to even binary files. They can be located in Google Cloud Storage, in Azure, in DBFS, in AWS. We have the checkpointing. As I mentioned, in case it fails, it resumes from where it left off. It's scalable, so we can ingest millions of files within an hour. And it's a very good option when we have to load files from cloud storage to the Delta Lake. Let's also see how this one works. And we have it here, where we'll load JSON files. We'll generate some JSON files, and we'll load to Delta table. Let's do again a quick cleanup. And here we create the bronze transaction streaming table. Okay, here we generate some JSON files. And as you can see, so this is a notebook that I imported directly because it was not part of the demo itself. It was easier like that. So I generated 5 JSON files. And this is how one JSON file looks like. We have transaction ID, customer ID, transaction date, and type. And each file contains 2 transactions. So 1, 2, then 3, 4, 5, 6, 7, 8, 9, 10, and this is all. So we have 10 transactions. Now, in order to read these files, we use the format cloud files and the JSON as cloud files.format. We provide a location for the schema. We provide a location for where the files are located. Here we add, here we do a cast of the transaction date, the timestamp. Then we select transaction ID, customer ID, transaction date, and type ID. These are the fields that we want to select. Then we write stream, format delta with a checkpoint, this time trigger available now, true, to table bronze transactions. So because in this example, trigger is available now, then it will process all the available data and then it will stop. Let's run it. So stream initializing, and then it stopped. Let's check what we have in the bronze transactions table, and we have all 10 transactions, as you can see here. Now, let's load more data. Let's generate another 5 files, so another 10 transactions, so from 6 to 10. With transaction 11, transaction 12, and so on and so forth until transaction 20. Good. Now, because we have set it in available now, we need to run it again because it stopped. Let's run it again. Okay, and now let's check the table. In our table, now we have 20 transactions. And the transactions that we processed previously, as you can see, we don't have any duplicates. Good. Let's return to our presentation. Now, because we discussed about the data ingestion from files, let's now discuss about the transformations. We have 2 types of transformations. We have stateless transformations and stateful transformations. The stateless transformations do not depend on any state, so we don't need to keep track of anything. Let's say we have select statements. We don't need to keep track of anything. It's just a select. We have the explode, or we have a filter. There's nothing that should be kept somewhere for future use. But in case of the stateful transformations, we need to keep track of some values variables, because the stateful transformations are the aggregations. Simple aggregations such as sum, average, count, or windowed operations, aggregations over a window. So it could be a tumbling, a sliding window, joins. And all these aggregations are all these values, part of the aggregation, are kept in the state. So this is why they are called stateful transformations. As you can see here, we have the read stream and the write stream, and the aggregation is between these two. When the aggregation is placed between the read stream and the write stream, this is a stateful transformation. And as you can see, we have here a group by customer ID. We have a sum for the accumulated amount spent, and we add another column, the total discount given at 10% of this accumulated amount spent. When placed here, it's a stateful transformation. However, I will show you actually in the next slide. Let's first show you how it works. This one, the stateful. We have the input batch, and we have the accumulated amount spent 100, 200, 300. Because it's the first batch, when we will aggregate the data, we'll get 100, 200, and 300 because it's aggregated, it's grouped by customer ID. But when we receive the second batch, as you can see here for customer ID 1, we receive 200. Now the total amount spent is 300. So it's 200 from here plus 100, the previous value. But this is not done programmatically, like to take into account the previous plus the new one. This is part of the aggregation. This is how it works, the streaming transformation, which is very nice. It takes care of everything. For customer 2, we have 300 and 200, the previous value, which is 500. For customer 4, the customer 4 is new. We got 400 and 400 is the value. And the discount 10% of each value of those. So it does this completely by using this aggregation here. But we can make this stateful aggregation stateless. And we can do this by moving the aggregation from here. In the for each batch, the for each batch allows us to write a custom function where we apply, let's say, complex logic or more complex logic. We have a lot of flexibility to the output of the micro batch. And if we place this aggregation in the method of the for each batch, will transform from stateful to stateless. And we'll have nothing between, we'll have no aggregation between the read stream and the write stream. So we can add in the merge here. In the function here, we can write the aggregation, then we can write the merge statement or anything else. Okay, because we discussed about the aggregations and the window operations, let's review two types of windows because we will have some examples. The tumbling window and the sliding window. There is also the session window, but I didn't add any example and it's out of scope for this presentation. The tumbling window means that we have fixed windows. They do not overlap, so they are continuous. They are one after each other. And they are used, let's suppose if we want to count the number of transactions every 10 minutes. So we have windows of 10 minutes, and we will count the number of transactions within this window. So let's say it's 10 to 10, 10, then 10, 10 to 10, 20, 10, 20 to 10, 30. So windows of 10 minutes that do not overlap. But the sliding windows, these are also fixed size, but they overlap. So we can count the transactions every 5 minutes over a 10 minutes window. So at every 5 minutes, we create another window where we will count the number of transactions that came in. And the transaction can come here And it will be part of this window and also of this window. It can be part of both of them. Okay, and because we discussed about these windows, we can have also events that arrive late. But the good thing is that sparse structure streaming allows us to receive late arriving data. So let's suppose this is the time, the arrival time. And these are the events. And the time from here is the event time, is the time when the event has been generated. Generated in the source. They can be generated in a Kafka topic. However, due to some issues, they do not arrive around this time, but they arrive later on. How can we, let's say, we can keep this late arriving data. However, is it that good to keep it indefinitely or not? Let's review this. So we have between 10 and 10:30, we have this event, which is letter A. In this example, this is a count of letters. With event time 10:02. So this event time is between 10 and 10:30. So it's not a late arriving event. Then we have this B and C, 10:34 and 10:58. This also came within their window. But between 12 and 20 and 12:30, we have this letter B, this event, which has the event time 10:04. 10:04, this means that this is a late event. It was generated at source at 10:04, but it arrived at 12. However, we can take it into account when we count the letters. So even though it is late, it is accepted. But if we accept all these late events, this means that we maintain the state because these are kept in the state and the state grows over the time, which leads to some out of memory issues. And in order to let's say reduce this risk, we can use watermarking, because watermarking will drop the unnecessary and old windows, because we don't need to let's say to inspect an event generated 1 month ago to arrive now. And even if it arrives, it will not be taken into account in any report because this is very, very old and everything was closed. For watermarking, what is watermarking? So its purpose is to drop and discard all those old events and to allow the events to arrive late, but only within a threshold. So the watermark is calculated as the maximum event time seen by the system minus this threshold. So let's go through the flow. When we have the event 0, then there is no watermark because there is no event that came before, so that we can take into account the maximum event time. But when the event 1 comes in, then we ask ourselves like this: is event time higher than the watermark? If it's not higher, then we drop the event because this is old. But if it's higher than the watermark, then we process the event. After we process it, there is another question: is the event time maximum? If it's maximum, then we set a new watermark, which is the maximum event time minus threshold. If the event time is not maximum, then we keep the existing watermark. And translating into the code, we have this with watermark. The field, the timestamp field, the event time, or it could be timestamp it's just the name of the field that indicates when the event has been generated at source. And the threshold, in our case, 4 minutes. Then we have a grouping by a window. This is the tumbling window of 4 minutes and the value. But this is the flow. The output mode is either append or update, and it will discard state for all windows. So this is how we will maintain a good size for the state and will not end up with out of memory issues. Let's take another example in practice. So we have 10 to 10:04. We have 3 events. All of them came within the window. 10:04 to 10:08. 2 events, 10:05, 10:07, both of them came within the window. Now between this window, 10:08 and 10:12, we received this event, 10:02. And 10:02 is discarded. Why it is discarded? Because 10:02 is less than the watermark. Watermark, in this case, is 10:03. Why it is 10:03? Because the maximum event time until this processing is 10:07. And 10:07 minus 4 minutes is 10:03. So this one is dropped. Then we move to the next one. 10:09. 10:09 is accepted because this one is higher than the watermark. Then 10:04. 10:04, again, it is dropped because 10:04 is less than the watermark, which now is 10:05, because after processing this event, the watermark got updated. So 10:09 minus 4 minutes, it's 10:05. So it gets discarded. And we have also this event, 10:07, which is also late, but is accepted because 10:07 is higher than the watermark. So it is accepted even though it is late. Now let's see in practice how it works. Okay. So we have again a cleanup. And here we have 2 tables. We have bronze events, a source table, and silver watermark results, another table. Let me create it. Okay, and we will read from the bronze events table into this streaming data frame. Then, this streaming data frame, we apply watermark to it with watermark on the event time with a threshold of 4 minutes, and we group by window and column. Window, which is the tumbling window of 4 minutes, and the value. We have a count and a select, the start of the window, the end of the window, the value, and the count. Here we have also the function for the for each batch, which means that we merge into the destination what we have in the micro batch on window start and value. And when it's matched, we update the count because we want the count to be updated within the window. We receive one event, another event, and so on and so forth. So we want to be updated. And when not matched, then we insert these values. And this is how we write it. We have watermark df, which is this one, that write stream, the output mode update, the for each batch, and the name of the function from here, the checkpoint location, the trigger available now, and the start. I said that there are some examples where we'll use start. This is one of them because we have the sync for each batch. We don't have table. And this one starts with start. Let's run it. can check also the query status, stream initializing. Okay, then it stopped. Okay, we have no results because we didn't insert anything. Now let's insert. Let's insert letter A with this timestamps. Letter A with 2 p.m. Again, letter A, 2 p.m. 05. Letter A with 2 p.m. 06. Letter A with 2 p.m. 09. After we insert these records and when we start our stream, the watermark is 0 because it has no event in the past that was processed to get the highest event time. So let's insert these records. Okay, and now we have this with available now. So we need to run it. Okay, the stream initializing. Okay, it stopped. Let's check the table. And we have all of them into the table. How do we have them? So we have the window of 4 minutes. Window starts at 2 p.m. and ends at 2 p.m. 04. And we have one record here, which is this one. Then another window that starts at 2:04 and then ends at 2:08. Here we have 2 records. 2 records means these 2. And between 2:08 and 2:12, we have one record, which is this one. Every time we process the data for the first time, everything will be inserted into the table because, as I mentioned, we have no watermark. So everything gets inserted. But now let's insert again letter A, and this time with 2 p.m. 01. Because the watermark after processing this data got updated and it's 209 minus the threshold, it should be 205. Let's insert this record. Okay, let's run again. Okay, and now let's check our table. As you can see, the record was not processed because it was not higher than the watermark. And this is how we can discard records that arrive late. Okay, let's get back to the presentation and let's talk about another important topic, joins. How do we perform the joins? Apart from the fact that we have several types of joins, it's important how and or what do we join. So we can join a streaming table and a static table, which will be actually the streaming data frame and the static data frame. And the other way around, the static data frame with the streaming data frame. And in case we want to join a streaming data frame with the static data frame, then we perform a stream static join and we have the inner, the left outer, and the left semi available. If we want to perform a static stream join, then we have the inner and the right outer available. But we can also join 2 streaming data frames. And in this case, we perform the stream join. By performing this join, because this operation is stateful, the stream static join is not stateful, this one is stateful, we can use the watermark Or in case of a left outer, right outer, full outer, and left semi-joins, the watermark and the time constraints are mandatory. For the inner, the watermark is optional. But this operation is stateful. Now let's take an example. What is a stream static join in practice? So we have this streaming table, the transaction table, and we have a static table, the transaction type table, and we want to perform an inner join between this table and this one, streaming and static, on the type ID. And here we have the output. Because the type ID 1212 is also here, these are the rows that are matching. So as of now, it behaves in the same way as the classic inner join behaves. However, if we add, after doing that processing, if we add a new row in the static table with the type ID 4, which matches the type ID from the streaming table, it will still not be added to the output table. Why? Because only matched records at the time the stream is being processed will be in the target table. So this record has been processed previously. Now, even though we add a new row in the static table, it will not drive the streaming table to update. The streaming part of the join always drives the join in this type of stream static join. However, in case of a stream join, this record will be part of the output, because in case of a stream join, future input data can match past input data. However, because it's a stateful operation, state can grow indefinitely. And here we need to use watermarks. Let's have also a quick demo on this. And it's this one. For the joins, first of all, the stream static join. The cleanup. Here we will create the transaction type table, which is static. We will insert these two values, 1 and 2, exactly as in the PowerPoint example. Then we'll create the bronze transactions, which is the streaming table. We will insert also here those 3 transactions with type 1, 2, and 4, exactly as in the PowerPoint. And we'll create also an output table with the transaction ID, customer ID, so the same schema as the input table. Okay. Then we read the data from the bronze transactions. So this is our streaming data frame where we have read the data from the streaming table. Then we use part.read, as I mentioned, to read from a static table. This is a static data frame. For the join, we have the bronze stream, which is the streaming data frame, dot join. Here we have the static data frame on type ID and the type of the join, which is inner. And here we have the select of the columns that we want in the output. When we write the joined stream to the output table, we'll have the joined df, this one, because this has the output of the join data, that write stream, append, delta, checkpoint location, available now, and table silver transactions. Let's write also this one. Let's run also this one. Okay, let's check the silver transactions table. And we have transaction 1 and transaction 2. And we inserted the data 1, 2, 3 with type 1 to 4, and only this to match the other table, match the values from the other table. Okay, but let's insert also this value with 4 in the static table. Now let's get back and run again the stream. Okay, and let's check again the table. As you can see, even though we added the type ID in the static table, the output didn't update because this was added to the static table and not the static table is the driver of the join in this case. This is just a select from the transaction type, just to show you that all of them exist. And now we have also an example with stream joins. Again, with a quick cleanup. Here we create the bronze transaction, one streaming table with 3 rows. Then another streaming table with 3 rows. So this is the transactions table. This is a customer table. Let's run this. And the join will be on the customer ID. The customer ID, which is the second field. From here, and the first one from here. Now we read from the first streaming table, from the bronze transaction. We read from the second streaming table. So we have the transactions and the customers. Transaction stream, join customer stream on customer ID, type of the join is inner, and the select of the columns that we need in the output. Then this join stream, write stream to the silver transaction table. So it's the same approach. The only thing that changes from a stream static join to a stream join is this read stream from here and the way it behaves. Let me run this. Okay, let's check our table. And we have transaction 1 and 2, because these are the matching transactions. Customer ID 1 and 2 with customer ID 1 and 2. It's the inner join. Now, let's add this record to the bronze customer with value 4. Let's run again the stream. So we have here the 4. Now we add it in the second streaming table. Okay, now let's check the silver transactions table and our record is here. So the behavior between a stream join and a stream static join, in case of an inner join, is different. We can see here that in this case, we added a new record in one of the streaming tables, and this record is part of the output because the streaming part drives the join. And in that case, with the static table does not drive the join. Okay. Let's get back to the presentation. This is the final section, so we're almost at the end. Streaming deduplication. Streaming deduplication refers to those cases that in the source system, let's suppose we have a Kafka topic, and then we receive a lot of events. Let's suppose we receive the transaction ID, the event time, and other fields. What if we receive the same transaction at the same time? We want to keep in our bronze row table only the transaction ID and its event type as unicity. We want to drop any duplicates. In order to do this, we can use the drop duplicates. This method allows us to do that. We can specify a unique identifier. In this example, transaction ID and event time, or just ID, or it could be a row level. We can add all the columns, and we can completely ensure that we don't have any duplicate rows. And we can do this by adding it that drop duplicates, and these are the fields that indicate the unicity. And we can have the watermark or not. Without the watermark, past records are kept as state, so the state will grow over time, and the duplicate record can arrive at any time. But if we specify the watermark, we can limit how late the duplicate record can arrive, and also we have the old state removed by the watermark. However, what if we want to ensure that when inserting some data, we don't create duplicates in the destination? What if we already have, even we deduplicate the data at source, but what if we already have some data in the destination, in the target table? If we want to ensure that we don't end up with duplicates in the target, we take advantage of the for each batch and we create a custom function where we perform a merge. And this is how we can assert the data. As shown here, we have the for each batch, the name of the method. This is the definition of the method, and this is the merge statement. So we can easily assert the data. The for each batch with the method, this method takes two parameters. It takes the microbatch df, which is data frame with output data of the microbatch, and the batch, which is the unique ID of the microbatch. And this way, we can ensure that we don't have any duplicates when inserting data to the target table. And apart from that, talking about the deduplication at source, the drop duplicates will ensure that we will not have any duplicates at those fields that we specify as unique. However, we cannot control, let's suppose we have the transaction ID, we have the event time, same transaction ID, same event type, and we have a type, which is different. It will drop one of them arbitrarily. But if we want to keep that row with the highest type, then we will not achieve this with the drop duplicate. We will achieve this by adding complex logic or logic, just call it logic, in this method. We can create a row number, and this way we can remove the duplicates based on that. Let's have also a quick demo. This is the latest one. Okay, on the deduplication. And as you can see here, we'll create a table, bronze transactions, and we will insert some values and duplicate values. These two are duplicate. We have same transaction ID, we have same time. The type is different. Here is 1 and here is 6. Same transaction ID and same time. So these two are duplicate. And we will insert into the bronze. We'll create also the destination table, the silver transactions. Let's first run this. Okay. Let's select the data from the bronze transactions. And here we have the data from the source table. It has duplicates. Now, we read the data from the bronze transaction to a streaming data frame. We rename the column, the quick transformation. Then we add the watermark, 30 seconds. And we add also drop duplicates for the transaction ID and transaction date. We have this upsert function. And we write to the silver transaction table with available now. Let's run this. Okay, let's check the table, the silver transactions. As you can see, data is being deduplicated. However, here we have type ID 1 and 2, but we also have type ID 6. So as you can see, we cannot specify this, it just drops the duplicates, but data is deduplicated. So for simple deduplication, drop duplicates is very good to use. Okay, now let's insert more data. And here we can also check the watermark because the maximum event time seen is this one at 12. And the threshold is 30 seconds. So the watermark is 11, 59, and 30. And we want to insert one record, which is generated at 11:59, which is late data before the watermark. Another one at 11:59 and 50. This is also late data, but within the watermark. And another one, which is on-time data. Let's run this. Okay, now let's run our stream. Okay, let's check our table. And as you can see, transaction 4 has not been added because it's late data before watermark. But 5 and 6, they have been added to our target table. Okay, this is it. Thank you very much for the attendance. If you have any questions, I am here to answer, or later on if you have any other complex questions. Thank you once again.
Let's see if we have more questions. It was a great session, Iuliana. In the meantime, Jen Joseph also joined us. So he is here in the chat. Okay, thanks a lot. Let me share my screen just to remind everyone about the community. Please remember to join the Future Data Driven Summit. You have the QR code. I gave you the link in the chat. This is the big event of the year that we run together with several few data platform user group. So thanks a lot, Iuliana, and we'll see you next time.
Thank you very much.
Bye-bye.
See you next time. Bye.